Today, what I'm going to talk is about study of momentum equations in 1 and 2 dimensions. And so the main motivation of this work is to study the atmospheric and oceanic turbulences, which we can think of as two-dimensional or quasi-two-dimensional turbulence. Quasi-two-dimensional because ripples or the vertical extents are much smaller than the depth. So we can think atmospheric and oceanic turbulence as quasi-two-dimensional and two-dimensional. And here we are interested in to study the effects of intermittency and the scaling effects of 1 and 2 dimensional turbulences. So the equations that we are interested in is the simple Navier-Stokes equation. So derivative of u in plus a nonlinear term with this is in 2 dimension I can think. Pressure difference and viscosity plus some forcing term, external forcing with the incompressibility condition. And if I go in 1 dimension, the equation becomes like this. So ux is the only component of velocity, and fx is the force, nu is the viscosity term, this is the nonlinear term. So first we revisit this is also called the Burger equation, this 1-dimensional equation. So we first revisit the Burger equation. Burgers. Oh, it's not apostrophe S, right?
No, there's no.
Oh, okay. I thought it's, okay. I'm sorry.
Burger is more nice name, but I think
Yeah. Okay. And first we will study Burger's equation, and then we will move to 2-dimensional Navier-Stokes equation to study intermittency and this multiscaling. So we have a 1-dimensional system, and the initial condition we have gave is sin x to the system, and initially we have taken our viscosity to be 0, and this is the kind of solution. So this is the initial condition. This is in velocity space. This is, I'm sorry for this is too small. This is in velocity space. This is the initial condition, and as time evolves, so this point moves to the positive x direction very fast. So this is the movement, and this point moves to the negative x direction fastest. So this moves, and this keeps on moving until there is a shock. And as the shock forms, then there are some oscillations happens in the code, and so then these oscillations, we observe these oscillations, and this has been observed in several papers also, that these phenomena is observed numerically. But if we add a very small viscosity, then these oscillations do not come. This shock eventually smooths out, and they become, these peaks try to come near by each other. So,
well, these are from your calculations, right?
Which one?
Calculations you have done.
Yeah. Oh, it's.
Take credit for.
Oh, okay. Yeah. Sorry. Yeah. So if I take some small viscosity, then once the shock forms, this comes down. This velocity actually comes down, and this slowly try to become linear. Horizontal. And this is also, these reference means I have checked these results with those references. So that's it. So this is also benchmarked with this thing. And now if we look at the structure function, as Shailendra was telling, so this is the spatial order p velocity structure function. So we can think this is the difference of velocity to the power p. So this p goes there, and for small delta x, we can break it in, suppose this we can think of as a derivative of the, for small x we can think this as a derivative, and so the pth power will be derivative to the power p, and at the shock point this will go as the delta x. So we can expand this s, I mean the order p velocity structure function in this form, and if delta x is a very small number, that to the power p, so if p is less than 1, then the first term will dominate, and for p greater than 1, the second term will dominate. So effectively we can plot for different p, we can plot a curve, and the plot should look like from 0 to 1, it will scale as p, and then it will be constant. And if we go to velocity space, in the k space, then we will observe, in k space there will be, this will act as a derivative for small x, so this will cause, for p equal to 2, this will cause k square. So k square means we can think that the energy spectrum will fall as 1 over k square. So this is something we have tried to observe. So this is in one dimension. So this falls as 1 over k square, and if we add we keep on adding the viscosity, then the rate of falling increases at higher wave numbers. So we can tell that viscosity acts on higher modes of wave numbers, that is in small scales. So here viscosity has acted, and that has forced the full spectrum to come down. All these simulations are at the same time. And we have calculated the different exponents for order p calculation. So this is for p equal to 0. This one is for p equal to 1. Next, this one is for p equal to 0.5. This is for 1. This is for 2, 3, 4, etc. And we have taken, in this inertial range, we have taken the slope and have plotted this curve. And this goes as we expect. This from 0 to 1, it should scale as 1, it should scale as p, and then it should be constant. So this is not exactly seen, but we can think if we increase the system size, or if we increase the spacing of the time spacing, then we can observe this exact scaling. And effectively, in this reference, they have observed this kind of plot with a small, instead of having exactly smooth curve, I mean exactly 0 to 1 p scaling and 1 to further 1 scaling, they have observed some very small deviations from that, which is, we can think as multiscaling or something like that. Now, we have added a forcing term also to this system. The forcing is Gaussian in nature, and we are perturbing every mode with some force, but the amplitude of perturbation falls as 1 over k. So the higher modes are perturbed with a very small amplitude, and the lower modes are perturbed with a very small amplitude, and the higher modes are perturbed with a very high amplitude. So this perturbation is external in nature, so we should observe some intermittency. And so it starts from 0, then grows for a very small time with some amount, then keeps constant with giving and taking the energy from external source. So this is, we think this to be something like intermittency in one dimension. And then we have plotted this is the velocity and the noise. This is the noise is the 1 over k spectra noise. So this is the blue is the noise and red is the velocity. And here also we have plotted the order p velocity structure functions. So this is for 0, this is 1.5, 1, 2, 3, and so on. So these spectra are observed also in these references. And now we move to two-dimensional turbulence. We take a cross product for the Navier-Stokes equation with the Navier-Stokes equation, and we get this equation. And here omega is the vorticity and psi is the stream function, and the u is defined in this way. U is the velocity. We give the initial condition like this. So here also we are giving very low omega to the higher modes and very high value of omega to the lower modes. And the energy spectra, we'll have to get a k-shell averaged energy spectra. And since it is in 2 dimension, we expect the energy spectra to fall with k-3 slope. And here this is at time 0, and then with time it increases, and after some time it attains k-3 scaling. But there are some bugs. I still think that in my code there are some bugs. So the time that in which I have reached it at this scale, this is too much. So I think in my code there are some problem that there is some problem in time pushing to get this scaling. So this I have to still fix. I do not know where is the problem occurring, but the scaling we can observe from here, that's true. And if we add some small viscosity, then it does not get enough time to, this viscosity is actually very high. If we add some small viscosity, then it takes even longer time to reach that scaling. And if I add more viscosity, then it doesn't get enough time to get all the modes, that amount of scale in vorticity transferred, but it damps before all the modes get the energy. And if we take an initial condition like this, sin x and sin y, with some small viscosity, then this is the initial at time t equal to 0. So these are the positive value of omega. This is the sin x sin y curve in 2 dimension, and slowly it smooths out with time with this kind of viscosity. And this is we have shown the decay of vorticity with time, you can expect. And with different viscosity, we have plotted the total energy to check how does the total energy changes with viscosity. So this is for 0 viscosity, intermediate, and these are for very high viscosity. With time, this flows like this. And these are the references I have used. So these all these references that I have used, these are here. So this not all, these are also the references. And I acknowledge the organizers, my guide, my project guide, and my friends for support, and to ICTS for such a homely atmosphere. In this case, the f is 0, and in the next case, f is not 0. Ut plus ux is equal to, if in case of 0 viscosity.
Mu is equal to 0. Mu is equal to 0.
Yeah.
Okay. So this equation is basically dispersionless chemical Witten type equation.
Sorry?
Dispersionless chemical or Witten type equation.
Okay.
Because dispersion comes with either a and that was done. So it has, what are the features you have shown us? There is a jump.
Shock. Yeah.
And you tell me where it will become. I want to know that whether you learn on those results.
I do not know for Rankin Hugoner. No, I don't know.
Number 2. Okay, number 2. You know there is integrability structure in that equation also.
So if I use nu, then I can solve this equation exactly. If nu not equal to 0.
If nu is equal to 0, okay, sir.
nu not equal to 0, I can solve exactly.
I was asking nu equal to 0.
You are asking nu equal to 0. Okay. For nu equal to 0, I do not know.
You can solve it for zero.
No, in the solution, nu comes in the denominator. So if I put nu equal to 0, then it blows up. So
You can do this Kohl-Hopf transform.
yeah, Kohl-Hopf transform.
Linearizes the Burger's equation.
So if I use nu,
So that's what I'm trying to know from you. You use the Kohl-Hopf transformation.
but that is for nu not equal to 0.
Yeah, but then you take the limit of nu.
Oh, limit. Okay, right. Yeah.
Okay.
No, but sorry.
Yeah. So how is it? I mean the.
No. Okay, let us.
No. So just to summarize in the language maybe that he and I use. So what they're talking about when you take finite nu, do the Hopf-Kohl transformation. You can write down data.
No, I have the transformation here. Yes.
That's great.
Yeah.
And then you can look at the solution. You going to 0, and you have the answer. You can do a saddle point, etc., to get the answer, and then do the entropy solution with that. But more curiously, what you are saying about the integrability actually sort of becomes a moot point, because when you put nu equal to 0, and a keyword which would have solved, which he missed when he gave the nu equal to 0 bit, if then you make a Galerkin projection, so you take the PDE out, put it in a finite dimensional subspace, which is why after T star, you don't have any shocks anymore. What you end up is with an equilibrium solution, which Mitra and others were talking about the stochastic sort of approach to looking at climate.
So that was I was trying to whether he knows the Galerkin, all this
You have coffee?
You can discuss this with Partho.
Yeah.
Just one observation. Just for your sort of knowledge, this is very well-known equation in StatMech called the Kardar-Parisi-Zhang equation,
KPZ.
which is essentially the same as the Burger's equation. It's a noisy version of the Burger's equation.
Okay.
You may want to check out some of the literature. It's called the KPZ equation. I mean, it's very famous as a matter of fact, and there's a huge amount of work on that. Not solvable, but and there are a lot of controversies still regarding growth. It describes the growth of a fluctuating interface, basically. The KPZ equation is supposed to describe, but it's the same as the Burger's equation, but with noise added on, basically. And there's lots of interesting physics out there.
You take the u there and write it as the gradient of the field, and then you'll get a mod
Okay.
squared term instead of the
Yeah, definitely. Thank you.
There are other closer neighborhood of those equations, Dhrubaditya, these things, those things. Just check out all those equations, try. This will be something interesting.
Burger's equation is one equation that is a soliton equation and not a soliton equation.
Because this.
It's integrable, but it doesn't carry solitons.
But it starts being integrable when you are in the projected.
That's the point.
Basically, what happens is it's integrable because all these conservation laws go through all UN moments. The minute you project it, only the first three survive.
Exactly.
So the PD structure, this is one interesting case, which is not so common for the 3D Euler. It's a bit harder to do because it formally is like the Euler. Is the minute you do that projection, you can formally see the conservation laws vanish. And after that, you can use only equilibrium statistical mechanics. So you have Gibbsian ensembles, so those oscillatory structures are all Gibbsian structures. And that sort of emerges, which is, that's why, just to connect with the theme of the meeting, that's where all the sort of climate and sort of predictability.
It's very rich, actually.
It's a lovely equation.
Lovely equation.
There's even a book on this. It's called the Burger's equation.
The monograph by James Burger, have you read? It's a beautiful 40-page. It's in the IC library.